This video is a continuation of the matrix notebook, and we're going to be discussing some of the facilities that R provides for operating on matrices. In these examples, I'm not going to go into details of the methods or algorithms used by the functions we're demonstrating here, nor am I going to comment on their uses. These functions are given here with sort of a minimal example to give you an idea of what is available, and then I'm going to leave it up to you to discover the details of these functions and how they may or may not be used in your projects. So to get started, let's create a matrix to play with. And notice here that I'm only going to specify a single dimension rather than both the rows and columns. The matrix function, when you give it only one value for the dimension, will assume that you want a square matrix where both the number of rows and the number of columns are equal to the passed value. And now if we want to transpose this matrix A, we use the function T, which is short for transpose. And so we see in the output here that the first row was the first column in the previous output. Thus, the T function effectively swaps the rows and columns, performing the transpose. Now, also, we can use the array permutation function, aperm, to do this as well. However, when using this function, we need to specify how we want the dimensions to be permuted. Again, I'm going to use the print function to save on a little bit of space. And now I'm going to call the aperm function, pass the matrix A, and now I have to pass a vector of indices which specify the order in which the dimensions are to be permuted. So when I write 2, 1 here, I'm taking the columns and swapping them with the rows. Right? I'm taking the second dimension and swapping it with the first dimension, performing the transpose operation. And you see in the output, it matches the previous T function output exactly. A common operation that's done with matrices is multiplication. And for matrix multiplication in R, we use the operator %, asterisk, %. It's important to know that using the asterisk by itself, without the percents wrapping it, does not perform matrix multiplication. Instead, it performs element-wise multiplication. So to see this, let's create a couple of simple matrices. For the matrix A here, I'm simply going to give it the values 1 through 4 in that order. And this will be a 2 by 2 matrix. For the matrix B, I'll give it the values 4 through 1, so the opposite order from A. And again, this will be a 2 by 2 matrix. And now we can multiply A and B using the %, operator as follows, and we'll print this output. And to show you the difference with the asterisk operator, I'm also going to print the output of that operation. So I put print A asterisk B, and we see that the values we get here are different. In the first case, we get the actual matrix multiplication of A and B. In the second case, we're getting the element-wise multiplication of A and B. If we look at the elements of A here, we see the first element is 1. And if we look at the elements of B, we see that the first element here is 4. And 1 times 4 gives us 4 here in the output. Similarly, 2 and 3 gives us 6, and so on. And so we see that the single asterisk operator gives us element-wise multiplication, whereas the %, will actually do true matrix multiplication, which is what we want in this case. The next function I want to show you is the diagonal function, which simply returns a vector containing the diagonal elements of the passed matrix. So if we recall the matrix A, the elements 1 and 4 sit on the diagonal, and if I call diag with matrix A as an argument, I get back a vector containing exactly those elements. The determinant of a matrix can be computed using the determinant function, det. Or you can use the determinant function, spelling out the word entirely, to return the modulus of the determinant. Now I'm setting the logarithm argument to false here, so that it does not automatically take the logarithm of the result. Now for more information on determinants, there is a link here to a page written by Michael Friendly on the R project website. You can also check out the built-in help by typing help det, which will provide details on both of these functions. Now, R also provides functions for solving linear systems. Let's say we were given the linear system here, and we wanted to solve for x1 and x2. We would first create the matrix from the left-hand side, namely the 1, 2, 3, and 4, as well as the vector on the right-hand side containing 17 and 39. So we'll do that now. We're going to call our matrix on the left-hand side A, and we'll assign it the values 1 through 4. This is, of course, a 2 by 2 matrix. and we're assigning the values to this matrix by row. So we're going to set that argument to true. For the right-hand side, we simply need a vector containing the two values 17 and 39. And now we can call the solve function by passing our matrix and the right-hand side to the function to get the solution x, containing both x1 and x2. And we'll, of course, output x. And we see that we get the results 5 and 6 for x1 and x2 respectively, which can be easily verified. The solve function can also be used to compute the inverse of a matrix if the matrix is passed as the only argument. So if I write solve A here and output it, we see we get the inverse of this matrix, which we can verify, of course, by multiplying with the original matrix. So let's do that. And we see that the solution to this is something very close to the identity, at least within machine precision. Okay, so we also have functions for performing these squares. For example, let's say we're given noisy data at fixed x positions coming from the line y equals 2x. But let's say that we didn't actually know that the true function was y equals 2x. And so our job is to compute the least squares approximation using only the noisy data. So we can create our x and y input vectors using the given data, just as we would create any other vector. Let's say our value x was given at the points 0 through 4. And for our y data, let's say we were given these values here, which I'll simply paste. And now all we need to do is pass these vectors to the function lsFit. And the output, while containing much more information about what the algorithm actually did, it will contain the coefficients attribute that we see here at the top, which in this case contains an intercept of negative 0.018 and an x coefficient of 2.003, which is somewhat close to our goal of y equals 2x, given that we had noisy data. So for more information on using least squares and this particular function, to check out the built-in help, as well as section 5.7.5 in an introduction to R. And of course, I've given you this information here at the bottom of this section as well. Now, R also includes several common decompositions. So to wrap up this notebook, I'll briefly show you QR decomposition, how you can get eigenvalues and eigenvectors, as well as SVD. To perform a QR decomposition, you simply use the QR function and pass to matrix A. And the output will contain the lower triangle Q and upper triangle R in the QR output matrix that's seen here at the top. It will also include the matrix rank and some information on the pivoting strategy that was actually used in the decomposition. The eigenfunction can be used to retrieve both eigenvalues and eigenvectors for a given matrix. So for this example, I'll simply create a 3x3 matrix. And then I'm going to use the eigenfunction and pass our matrix A to this function. And when we run the code block in the output, we see the decomposition. We get values, which are the eigenvalues. And we get vectors, which contain the eigenvectors for this matrix as well. For more information on this, you can use the built-in help eigen, or look at section 5.7.3 in an introduction to R, and I give you a link to that section here. And finally, the last example here is for singular value decomposition, or SVD. Calling the SVD function on an input matrix A returns the vector containing the singular values from the diagonal matrix in decreasing order. It also returns the left singular vectors U and the right singular vectors V. And again, I'm giving you the link to section 5.7.4 covering this in an introduction to R. And of course, you can check the built-in help on SVD